Move it on down the road a little bit with some tougher trig equations. You really want to have these down if you're going to do calculus, because they pop up all the time in calc. So we're going to put a lot of different thinking in on this. I'm seeing, well, for one thing, if I think about this as far as a graphical approach, I see a sine function with an amplitude of 2, and I also know there's some period change, because that b number is something other than 1. So if you remember back when we were doing all the graphs, 2 pi over the period was how we found out the b number for our equation. And if we were given the equation to find the period, we just treated this as a proportion. So 2 pi divided by the b number will be the period. So in this case, we know the period is, 2 pi divided by pi over 3, which is the same as 2 pi times 3 over pi. The pi's cancel out, that'd be 6. So it's going to be a lot more. There's going to be a lot of this is let's see, normally the period for sine is what, 2 pi, and that's like 6.28. So this has been shrunken up a little bit. It's not quite as wide, so it's been compressed horizontally. So we've got to kind of keep that in mind when we're finding our solutions. So then, first off, let's solve this. What I'm going to do is I'm going to pretend this is just x, or u. If I want to, I can do what's called the U-Substitution. And I can think of this as just 2 times the sine of some expression u equals root 2. And then if I isolate the sine, so sine u equals root 2 over 2. And then you got to think about, oh, well, that I know all the reference angles that have pi over 4, and we work with the radian measure here. We don't want to change it to degrees. Pi over 4 has a sine of root 2 over 2, and I also know that the sine is positive in quadrant 1 and quadrant 2. So this is pi over 4, and that reference angle is also pi over 4. But this angle here is going to be 3 pi over 4. So that tells me, if I think about the arc sine, so a couple of ways to do this. I'm looking at it graphically. I'm saying an angle, so the angle's rotation where the sine equals root 2 over 2 is pi over 4 and 3 pi over 4. You could also think of this as the arc sine. In order to isolate the u, you're going to do the arc sine of both sides of this equation. Arc sine. And in that case, that's going to tell me u equals pi over 4, and u also equals 3 pi over 4. Now, the thing to keep in mind to make sure you get all your solutions is to think about, what if we were finding all solutions? In the book it says, do this on 0 to 2 pi. We're only supposed to find the solutions on 0 to 2 pi. But when the period changes, you could increase your number of solutions. So what I think the best bet is to think about, how do I find another angle that's coterminal to this positive angle? Well, I have to add 2 pi to it to get back to it. So 2 pi plus 2 pi k. And then to get back to the 3 pi over 4 again, I got to go all the way around again. So plus 2 pi k. Now, what I haven't dealt with is my U-Substitution, where I said u is equal to the pi over 3x. So we're going to have to take care of that next. So I rewrote that expression with the pi over 3 times x. So to isolate the x, because we're trying to find the solutions, I'm going to divide by pi over 3, which is the same as I'm multiplying by 3 over pi. And I'm going to have to do a little bit of distributing here. And I'm going to do that same thing with this side, with this other solution. So 3 over pi times 3 pi over 4 plus 2 pi k. And if I distribute this through, I'm going to get the pi's cancel out, so I'm left with 3/4. And the pi cancels out, and it gets multiplied by 3, so 6 times k. So that's what x can be. Those are all, that describes all solutions. And the same deal here. We're going to do some canceling out. That's going to give me 9/4 plus 6k. And now, because they're looking for solutions on their intervals 0 to 2 pi, what I have to do is I have to keep adding on these numbers until I reach 2 pi. Well, for this first one, if I add 6 to 3/4, that's going to be 6 and 6.75, which is already more than 2 pi. So the only solution for the 3/4 one is that. And it looks like for this problem, it's exactly the same situation. 1 1/4 plus 6 will be 7 1/4, so that's too big already. So it looks like there's only two solutions for this equation. So I could have almost got away without doing this 2 pi k trick. Won't always work that way, so that's why I wanted to show you right from the get-go about it. Now, using Desmos.com, I double-checked. I just wanted to double-check and see if I did get those answers. And as you can see on the interval, so I'm graphing this function here. On that interval, 0 to 2 pi, it does only cross the x-axis at 3/4 and at 9/4. So I was correct. So in this one, it's a little bit different. One thing, as it says in the textbook, you want to resist the urge of dividing both sides of this equation by sine t. Because what you do when you divide by a variable like that, or a function, it's like if I have x squared equals 6x, say, a simpler question. The correct way to do this equation is it's a quadratic equation. We're going to set it equal to 0 and factor out a common factor. So this parabola crosses the x-axis at x equals 0 and at x equals 6. If we had divided both sides of this equation by x, I would have lost the x equals 0 possibility. So that's why we don't want to divide by variables or by expressions like this. Okay, you want to try to do the isolation factoring and that kind of thing. So what I'm going to do with this one is I'm going to set it equal to 0. I'm going to bring all the trig ratios onto one side, and because I've got that negative 3 sine t, I'm going to move that to the right hand side. Plus 3 sine t, and then I look at this expression, I notice I can take a 3 out as a common factor. I can also take a sine t out. So when I factor out a 3 sine t, what's left? Well, 5 times 3 times 5 is 15. I have a cosine of t. And then because I factored out the whole thing, the 3 sine t, I've got a 1. And that's equal to 0. And then you got to ask yourself, where does 3 sine t equal 0? Where does 5 times the cosine of t plus 1 equals 0? So we know sine of t, if I divide both sides by 3, the sine of t equals 0. Where does that equal 0? Well, if you think about the unit circle, if you need to, sine equals 0 at 0. It's also equal 0 at pi. It's also equal to 0 at 2 pi. But since we're trying to solve this on the open interval, closed at 0, open at 2 pi, you won't count the 2 pi. So 0 and pi are two solutions. Then when you come over here to this one, we're going to ask ourselves, where does the cosine of t equal negative 1/5? And then because of that, what you're going to do is, because that's not a nice neat number, we're going to do the arc cosine of both sides of this equation. And when I grabbed my calculator earlier, I came up, the calculator told me 1.7722. So I know the cosine is negative in quadrant 2 and in quadrant 3. And the arc cosine function, you got to remember, gives me output between 0 and pi. We just studied that back in chapter 5, chapter 6. So this is where the 1.772 that the calculator told me. So in order to find, so that is one solution. That's that one angle, that's fine. But we also know this cosine's negative down here in quadrant 3. So in order to find that angle, what we need to do is we need to find that reference angle. And because this is in quadrant 2, what we're going to do is we're going to do pi minus the 1.772. And that'll tell me that reference angle. And then to get this full angle, we're going to do pi plus whatever that reference angle is. And let's see, when I did this earlier, I came up with this expression was 1.3694. And I'm going to add pi to that, or 3.14, so I got t equals 4.511 was the other solution. So then I really want to think about also if there are going to be more solutions than just these two here, plus those other two that I found. So when I think about the only way I can get back to this angle is to go all the way around again. That will make an angle larger than 2 pi. So that's outside the range. And the same thing here. I'm gonna go around again. That'd be bigger than 2 pi. So there's only going to be the 4 solutions. There's going to be 0. There's going to be 1.7722. There's going to be pi. And then there's going to be 4.511. So those are the 4 solutions to this trig equation. So again, I graphed this out at Desmos. There's my 0 solution. There's my pi solution. And what I did with this one is I just set the 2 equations equal, and I'm looking for the intersections. I could have set one equation all equal to 0 and then found where it crosses the x-axis. I just chose to do it this way because that's the way I felt like doing it. So no right way or wrong way. But there's a solution because they intersect there. Here's the solution. They intersect there, and that's the 0 and pi I got. And here's the 1.772, and here's the 4.5772. And see, they do intersect at 2 pi, but again, that's outside the range because we don't want to include 2 pi. So that's a check. Okay, so here's number 16, and we've seen a secant function, and we're trying to solve this. There's also some kind of period shifting going on, or some kind of period change. So how do you solve this kind of equation? Well, I know one thing I want to do is I want to say that I'm going to get rid of the 2 theta for a minute. I'm going to say this u. I'm going to do some kind of little U-Substitution here. So I'm going to say the secant of u equals 3. And then I don't like working with secant if I don't have to. And I know secant's the same as the reciprocal of the cosine. Okay, and if I want to solve this for cosine, I can just treat this like a proportion. And I can say, whereas if we do the cross products, so the cosine of u equals 1/3, and that should be fairly easy to solve. I don't know, 1/3 isn't a nice number, one of the nice, pi over 4, pi over 3, pi over 6 values. So I'm going to use my calculator, and I'm going to do the arc cosine of both sides of this equation. And my calculator tells me that u equals 1.231 if I do some rounding. And then I've got to remember the cosine has a positive answer there. It also has a positive answer down there. So this is one solution, and this will be another solution. So in order to find that blue angle, I got to remember, the reference angle will be the same as that angle is there. So to get that blue angle, I'm just going to take 2 pi and subtract 1.231 from it. And if you give me a second here on my calculator, I can do this. I'm getting 5.052. So that's a possible answer. That's a possible answer. I'm going to have to deal with the 2 theta next. So if I divide both sides of this by 2, as a matter of fact, why don't I add 2 pi k to this? Because there is a period change, and it might give us more solutions than just the 2. And do you remember why I have the 2 pi k? Because in order to get back to those solutions, I got to go all the way around, one whole revolution. So that's going to give me theta solutions of 1.231 divided by 2 of theta can be 0.616 plus pi times k. And theta can be, let's see, 5.052 divided by 2, 2.526 plus pi times k. So are we going to have any more solutions? Well, I'm trying to find all the solutions in 0 to 2 pi. And if I add pi to that, that's going to be less than 2 pi. So what's 0.6155 plus 3.14? That's going to be 3.756. And if I add 3.14 to that again, that will be bigger than 6.28. So we're done. Those are 2 answers. And then to this one, if I add 3.14 to that answer, I think that's less than 6.28, which is 2 pi, right? That's going to be 5.666 the way I rounded. And again, if I try to go one more time around, it's going to be bigger than 6. So those look like those are the 4 solutions. And looking at what Desmos.com gave me, I had it graph the secant graph and y equals 3, and then I looked for the intersections, and we can see those 4 solutions. Okay, so I'm okay. So number 20 is another little bit of a twist, and one reason I wanted to do this is I want you to point out to you that when you write a cosine squared or sine squared or a trig function to a power, you can think of it also as cosine theta, the whole thing squared. And then to solve this for the cosine of theta, I'm going to take the square root of both sides. What am I doing here? Equals the square root of 1/2, which is the same as 1 over the square root of 2, which rationalized becomes root 2 over 2. And then we ask ourselves, actually I got to do a plus and a minus, right, because I took a square root. So let's ask ourselves, where's the cosine equal to positive root 2 over 2? Well, 45 degrees, and at down in quadrant 4, when that's also 45 degrees, or pi over 4. And then where's it negative? Where's the cosine negative? Over here in quadrant 3, where's pi over 4? Let's see, this is pi over 4. This is pi over 4, and also down here, this is pi over 4. So what are the answers? Well, one angle is pi over 4. The next one is going to be pi minus pi over 4. So 3 pi over 4. Why did I write 2 here? Just a minute here. Not let me change it. Okay, so that's going to be, oh, look at that, I wrote 2 again. Those should be over 4. And then this one down here will be a 1/4 of pi more than pi. So that's 5/4 pi. And then this other one will be 7 pi over 4. And those are the 4 solutions for this. Well, that's really a quadratic equation. So here's another trig function, which is in a little bit different form. Some people like to get rid of the, actually let me write it this way. It is a quadratic equation, so when we solve quadratic equations, we want to set it equal to 0. So I'm going to move the 3 and the minus 2 cosine theta to the left-hand side to set the whole thing equal to 0. And now what I'm going to try to do is factor this. If I can't factor it, I got to use a quadratic formula. or completing the square. Some people have a hard time with having the cosine in the mix. So what you can do temporarily is say, okay, so u equals the cosine of theta, and you can rewrite your trig function like this. Now, it's perfectly alright to leave the cosines in there because it saves you a step. But if you're having trouble doing this, we should try to. You can do this little substitution to help yourself out. And then I am going to try to factor this. I have no idea if it'll factor. I'm going to try 8u, and 1u. And if I put 3 here and 1 there, oh, that's not going to work. So let's try 4 and 2. Maybe that'll work. So 4u and 2u. Let's see, that's going to be, oh, I think we've got a solution here. Let's see, that would be, this would be 6u. That would be negative 4u. 6 minus 4 is positive 2. And we get negative 3. We're good. That's how that factors. So then I can say u equals negative 3 over 4. I can say u equals 1/2. So what I did is I replaced the u's back to the cosines. And let's try to work on this one. Where does the cosine equal 1/2? Well, the cosine's equal to positive 1/2 in quadrant 1 and quadrant 2. And if this is 1 and this is 2, and that has to be the root 3, which makes this angle pi over 6. And yes, you can use a unit circle to figure that out. I'm hoping you'd stop having to use a unit circle. And since that angle is, whoops, I wrote pi over 6 and it should be pi over 3. At least I caught myself. Pi over 3. And since this angle has the same reference angle, 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. So there's one pair of solutions. The other one, I don't know what angle has a cosine of negative 3/4, but I do know that that is over here in quadrant 3 and in quadrant 4. So I'm going to grab my calculator and I'm going to do the arc cosine of negative 3/4. And that's given me 2.419. And of course, as we saw in that other video, or the other exercise, I have to find the reference angle, then add that to pi. So pi minus 2.419, and then I'm going to take pi plus that answer. So pi minus that answer, I'm getting 0.7227, and then I'm going to add that to pi, and I got 3.864. So that's a solution, this is a solution, and these two values are solutions. This one specifically because they're mixing up sine and cosine. It really works slick if there's only one trig function in this mix. So if you think about that Pythagorean identity, I can say that sine squared theta is equal to 1 minus cosine squared theta, and then as you see, we've got a quadratic equation. If I add cosine squared t to both sides of this equation, and then I try to factor this, well, I don't think this is going to factor because there's really no way I can have products that equal -1 and just have a 1 cosine t. So this requires quadratic formula, and so what I'm going to do is, oh, maybe I should do this to help you out. So u squared plus u minus 1, if I say u equals cosine of t. So now just use a quadratic formula. I mean, I could do this by hand. I encourage you to, this is a pre-calculus class, so I encourage you to use the polynomial solver. That's what I'm going to do. I've got one built into my calculator here, and I've got a 1, 1, and -1. So this is telling me that u is equal to negative 0.618, and u is equal to Actually, that's positive 0.168 and negative 1.618. And then I'm going to do that back substitution, cosine. So I'm going to say the cosine of some value equals 0.618. And the cosine of some value equals negative 1.618. Then we got to worry about how some extraneous roots here, because cosine is never going to be more than 1 or less than negative 1, so this has no solutions there. So we've just got to worry about whatever solutions are going to come out of this. So I know the cosine is positive here in quadrant 1, and it's positive down here in quadrant 4. So those are the two answers we're going to find. Now if I do the arc cosine of this, that'll tell me that angle in quadrant 1. So second cosine of 0.618, I came up with t equals 0.9046. And of course this reference angle will be exactly the same, and they're looking between 0 and 2 pi for solutions. So I don't want to say negative 0.9046, so I'm going to have to take that value away from 2 pi. And that'll be that other solution. And you can always graph it to make sure you're right. So 5.379 I'm going to round to. So those are the two solutions on 0 to 2 pi. And I think that's enough examples. This video is probably long enough. Give some more problems out of the textbook a whirl, and then try your MyOpenMath.